All right, that's it. So good morning, everyone. This is the tutorial number 12 now. So before starting, let me just introduce you a book I like very much. So it's called Pierre Gilles Degenne's Impact on Science. It's actually a collection of articles by himself. This one is volume number 2, dedicated to soft matter. There is another one for other topics. What is very nice is that you find for each article then an explanation by a physicist who is related to the topic of the article. So you have really the core brute article and then explanations on what's inside and the impact. So you already got an example of that with the n=0 theorem, for which I gave you a 20-page explanation by Tom Wheaton on the impact of that n=0 paper. Okay, so it's taken from this book. So I encourage you to have a look. It's very interesting, especially on how to do science and how to do impactful research. And then today we are talking about an article by Webster and Cates. So it's about chemical potentials and emulsions. And in particular, here they want to consider the importance of trapped species within emulsions. So you know, emulsion is a collection of, let's say, oil droplet in water, for instance, or a certain fluid in another one. There are surfactants that can stabilize those emulsions, but you can also put some colloids or any particles inside the droplets to stabilize them further. We would like to understand that. In fact, if you are interested in cooking, the French vinaigrette is working this way. So you are mixing two fluids that don't like each other, oil and water. So if you don't do anything and you just put your vinegar and your oil and you wait for a day, then you have a separation of phases. So you need to bring energy to fight against this and create some emulsions. And then what you do, you put some mustard, typically, so you will add some species, and you also add some salt. And salt is a charged species that will like water, but not oil droplet due to the polarity of the fluids. And therefore, you can stabilize them further. So we would like to understand, beyond the surfactant aspect related to mustard, what is the effect of salt here. So it's a very nice article by Webster and Cates, and basically we will do exactly, we follow it with the same calculations. I just transformed it into a tutorial as usual with intermediate steps so that we can follow everything. All right, so please take this with you. We are going to start now. Let me share the whiteboard. All right. Okay, and so we are ready to attack. So first of all, let us consider the following system. We take a U shape. So you know really this demonstration of osmotic pressure. You have a U shape like tube, which is this way. Here you put a membrane that is permeable to water, but not bigger species, let's say oil molecules, for instance. And what you do is that you prepare first on the side a microemulsion. So this is a microemulsion. So inside you have, in fact, a collection of oil droplets. This is oil inside water. Okay. And what you will say is that you will have a certain number, which is very large, of oil droplets. We assume that they are all equal, I mean, identical droplets. Of course, there is a polydispersity in reality. So we assume that they are each have a volume, which is the one of a sphere with radius A. So they all have the same radius. And we don't know yet the radius of such droplets, but we will calculate it. We put that at a temperature T, of course, and at a pressure, an external pressure, which is P, which is fixed here. And beside that, we assume that there is no volume of mixing. So to create that emulsion, we actually mix two volumes. We mix a volume of water, which is 20.5 milliliters before stirring, and then 1.5 milliliters of oil. And we stir, we agitate everything to obtain this emulsion here, okay? And we assume that there is no variation of volume, meaning that at the end, you still have 30 milliliters for your microemulsion. This is not completely true. You, in fact, have a little change of volume due to the mixing, but we assume it's a correction, all right? And so what we do is that now we take this guy here, and we just pour it in this container, okay? And on the other side, we put pure water. So here we put pure water. And this is the emulsion. So 30 milliliter each. So initially you have the same volumes on the two sides, but due to the osmotic pressure, due to the fact that you want to dilute the phase where there is those oil micro droplets, there will be a change of height, and actually water will flow through the membrane, and at the end you will have a variation. So you really, I think, know this the demonstration of osmotic pressure, but you will have a certain height difference, which is a balance between the osmotic pressure that tends you to rise, and at the same time gravity that fights against this rise. So here you have your microemulsion here everywhere, several droplets. All right, so this is the system we would like to consider, and we would like to introduce the chemical potentials for water in both phases. We would like to consider the equilibrium situation and discuss a bit the osmotic pressure. This is just a simple first part. And then from that, we will study the behavior of real emulsions. All right. Do you have any question before we start? No? Okay, perfect. So the first question is to find the final volume in the first compartment. Okay, so this is pretty easy. You have here, I forgot to say that we assume this tube to have a diameter which is 1 centimeter squared, and so if you multiply this 1 centimeter squared times h, and h is what is we provided in the tutorial, I guess it's 5 millimeter. Okay, so you end up with 0.5 centimeter cube here, or milliliters. So that's the volume difference, but then in fact the final volume is with respect to with h/2, so it's 30 milliliters plus 1 centimeter squared times h/2, which is 30.25. Okay, so that's the final volume, and in fact it's not very different from the initial one, but there is an observable difference. Okay, and so now we would like to go in the details and calculate the reason for that. All right, so first of all, when you mix two species, so considering the left tube here, you have oil droplets in water, you will have, okay, so you have a priori a change of volume, we neglected it. You have a change of energy because you have an energy of mixing, and then you have a change of entropy because you have an entropy of mixing. You are putting several droplets into a big volume, so it's like an ideal gas of droplets, and there will be plenty of configurations for that, so there will be an entropy change. Can you tell me what is the energetic cost in this situation? So the energy of mixing. Why is there a cost?
Well, is there a cost because we create surface between the oil droplets and the water?
Exactly. Exactly. So it's surface tension that is the penalty here. And so if you have identical droplets that have a surface 4 pi a squared each, then you have a surface tension between oil and water that I call gamma, and I simply multiply this by the number of droplets because they are just additionally playing the game. Okay, so that's the energy of mixing. I call this delta E, or you could call that delta U if it's considered as an internal energy for you. All right. Then let us go towards the entropy. So we consider that the emulsion is described as a lattice. So it's in fact mostly filled with water, but you will have some places you will have oil droplets. So let's consider it as a simple lattice, and sometimes there is an oil droplet. Okay, it's pretty dilute. That's the picture. That's the standard picture when you want to calculate the entropy in such osmotic situations. And so we need to know the number of cases. So here in this drawing, you will have the number of cases, which is the total volume of your microemulsions divided by the volume of one droplet. So this is n. And inside this, you will have n dark cases. Okay, so that's the total number. So the number of configurations is trivial, is the one of an ideal gas, and so you have a certain number of configurations, which is obtained by combinatorics, finding small n within capital N positions, and this can be expressed with factorials number. All right. Very classical. We assume the number of cases to be huge. The number of droplets is much smaller, but it is still a huge number. Remember what we said here. We still have a large collection of droplets. Actually, at the end, you will see that it's much more than billion. And then, so the entropy of mixing will be obtained by this counting way. And then we have, if we assume that we have large numbers, we can use the Stirling formula. And so it's KB times n log n minus n log n. Sorry, I will use the log notation. It's still a Neperian one. This is the standard way. All right. This is the entropy of mixing. Any question? Baptiste, do you have a question, perhaps? No? Any question? No? Okay. So that's the entropy of mixing, and from the entropy of mixing, we can now calculate the enthalpy. The free enthalpy of mixing. So in this problem where P and T is fixed externally, the good ensemble is the PT ensemble, and so the free enthalpy is the good quantity, and it is obtained by well, the free energy plus delta PV. But the thing is that P is fixed, is the external pressure, the atmospheric one, and we said that there is no volume of mixing here. Remember, we said that we assumed that there was no change of volume when you put the two species together. Therefore, this is 0, and in fact, delta G is equal to delta F. So it's a situation where it doesn't matter if you are in the canonical ensemble or if you are in the PT ensemble. And so this is delta E minus T delta S. So we have everything to calculate this change of free enthalpy. So we have this N gamma 4 pi A squared, which is the energy cost, and then for the enthalpy, for the entropy, sorry. Okay. So we found the total change of free enthalpy, and so it's directly related to the chemical potential, so we can really move on now to that question. Is there an issue with that so far? Normally, pretty simple arguments is the ideal gas in the canonical ensemble. Okay. All right. Chemical potential. So we have, if you remember the tube here, which is a U-shaped tube, in this region, you will have water passing from the right to the left, and at some point, you will have a balance between the two sides and you will reach equilibrium. So at that moment, the chemical potential near the membrane should be the same on both sides, okay, for no macroscopic flow to occur anymore. I mean, no flow at all, by the way. Therefore, near this membrane, you need to know both the pure water chemical potential on the right side and also the water chemical potential on the left side, which is a priori a function of pressure and temperature. Okay. So we call this guy is the chemical potential of pure water at pressure P and temperature T. And so in the emulsion near the membrane, we would like to find the chemical potential of water. So how do we do that? We are interested in this guy in the left side of the tube. I want to calculate that. What should I do?
If I remember well, it's mu naught plus kBT log of a ratio of the concentration.
Okay, so you already have the result. That's right. But even from the if you don't remember that result, how is it related to what we did so far? What is the connection between the free enthalpy and the chemical potential?
It's the derivative regarding the number of molecules of the free enthalpy.
Yes, that is correct. So if I derive the free enthalpy that I just calculated, which actually I only calculated the change of free enthalpy. We will come back to that in a minute. But if I derive the free enthalpy with respect to the number of water molecules, everything else being constant, so the external pressure, the temperature, we are in the PT ensemble here, and of course the oil number of molecules, then I find the chemical potential of water. And we will demonstrate the law you just expressed, Baptiste. So to do that, well, we have to remember that G is in fact made of several contributions. So we have G of water, pure, before mixing, then G of oil, before mixing, and then delta G that we just expressed, which is the change due to the mixing. So mu of water will be basically the first term here, which is not depending on the number of oil droplets because this is a pure water case. Then there is 0. This doesn't contribute. There is no water in a pure oil phase. And then you have this contribution. All right. And the first term is nothing but the pure chemical potential. So in fact, the chemical potential is the pure reference plus a correction due to the mixing that we want to estimate. Okay. And so we know everything. We have delta G, which is 4 pi gamma n a squared minus kBT, and then n log n, and the difference. All right. So we should just do a little identification here. So this is the number of oil droplets. This is the total number of cases in my effective lattice. Remember the drawing here, okay? And this is the difference between the two. So we want to know where is water in all this. So N is the total volume divided by V. So let us just write it here. And the total volume is made of two things. It's made of the number of water molecules times the molecular volume of water, which is the volume of one single molecule of water, plus the number of oil droplets times the volume of one oil droplet divided by V. So here I introduced a new quantity, which is the molecular volume of water. So very small quantity here, it's molecular. Okay, so you see, this guy is simply an affine transformation of this guy with a slope which is Vm over V. So in the previous construction, it means that when I will derive delta G with respect to the number of water molecule, well, there will be a dependency here, and there will be a dependency here and here. Small n is the number of oil droplets. There is clearly no water molecule in the oil droplets. All right? So we can now calculate the total chemical potential. It's the pure reference. And then you have minus kBT. So here there is no water molecules. N is the number of oil droplets. So there is no contribution of the enthalpic part. And the entropic part, well, we will have two contributions. So kBT log N minus 1 here. And then if I derive this with respect to capital N, I have minus log N minus N plus 1. And then I should multiply this by the derivative of N with respect to NW, which is Vm over V. Do you agree with this result? Yes? Interrupt me if it's not clear. Huh? All right, so we have a cancellation here, and this ends up with the following formula, where you have minus kBT Vm over V, and then you have the log, I can put a plus, of 1 minus N over N. Okay? All right, and now we have an assumption that we expressed at this stage. We assume that it was not written, but I said it orally. We assume that this was a small number. Okay, so small n over capital N is a small number. It's a dilute assembly of oil droplets within water. And so this can be transformed into Baptiste formula, which is kBT Vm N over NV. Yes, I think Baptiste was stopped at the log, in fact, but we can simplify it further. This is the situation where you are dealing, in fact, with the chemical potential of the solvent. The log is here when you are dealing with the chemical potential of the solute. Okay, so there you would keep the log, but when you are dealing with the solvent, it's really present abundantly, and then you can tailor expand the log. Finally, we have a connection between N and the total volume. So N, let me find it here. N is capital V over small v. So this is equal to Vm times C, where C is the concentration of droplets. So you end up with the chemical potential of water, which is simply the pure chemical potential. But now that you have oil droplets inside, you have a correction, which is basically a Van't-Hoff correction, or ideal gas correction. You have KBT times a concentration, which is the concentration of droplets. And then to make it an energy, there is the molecular volume of water that has been removed each time an oil droplet is present. All right? So far so good. What we have done is that at equilibrium, we have found on this side of the membrane the chemical potential of water. On the other side, it's pure water, so it's even easier. But be careful, the pressure is not the same on both sides, so there will be a contribution of the gravity in the game. So that's the topic of the next question, I suspect. Yes. So now we would like to move on to the mechanical or thermodynamical equilibrium. So at equilibrium, you should have a balance between, on the left, the chemical potential of water at a certain pressure and temperature, and on the right, the chemical potential of water at a different pressure and the same temperature. And the difference of pressure, if we look at the drawing, is rather with an increase of pressure on the left side. So I put it with a delta P, which is positive here, because as you can see on the drawing, there is here more fluid. So you have a hydrostatic pressure, which is higher near the membrane on the left than on the right, okay? Assuming that the outside pressure is homogeneous and constant. Therefore, this is the equilibrium equation that you want to solve. And so let us put numbers. Delta P is the hydrostatic pressure, so it's the density of water. Typically, we neglect the correction due to the presence of oil. The gravity and h, which is the difference of height between the two compartments. And if I put orders of magnitude, this is 10 to the 3 for the density, like water. G is 10. H is, I said, 5 millimeters, so 10 minus 3. And so you end up with what? With 50 Pascal. And 1 bar is 10 to the 5, right? So it's much smaller than the external atmospheric pressure, P. So it's really a correction, this hydrostatic pressure. As a consequence, you can Taylor expand the left side. And thus you can write that mu of water at P plus delta P and T is in fact mu of water at P and T plus, it's an approximation here, delta P times the derivative of mu of water with respect to P at T, which is fixed. And remember one other thing is that mu of water, we are dealing with the left side of the compartment here. This is this part. And mu of water is here. It's mu 0 minus kBT VMC. Right? Therefore, in fact, this can be rewritten with only the pure chemical potential, mu of water pure, because there is no pressure dependency in this correction. All right? So finally, mu of water in the left compartment, which is slightly at higher pressure, is equal to, let me expand this, you have the pure chemical potential minus kBT VMC. I really expressed that term with the pure chemical potential, plus a correction that I would like to estimate now. this is the left side of the tube, and this should be balanced on the other side by mu0 at P and T. This is this equality here, the right side chemical potential. So this is equilibrium. Thermodynamical equilibrium. All right. So what do we see? First of all, those guys are neglected. I mean, balance each other. And so you end up with the following law, which is the fact that the variation of the chemical potential in the pure phase with respect to pressure at constant temperature is equal to kBT VMC divided by delta P, and delta P, remember, is rho GH. Rho GH here. All right. Now I wish to estimate the left side of this equality to terminate the process. So let me consider the pure phase. In a pure phase, you have the fact that G0 of water is equal to mu of water in the pure phase times the number of water molecules inside. So G is equal to mu n. That's an important relation in thermodynamics for the free enthalpy. And you have thus the fact that this is d mu times the number plus mu times the differential of the number. And on the other side, this is equal to dg that we know. Dg is minus s dt minus plus v dp and plus mu dn. Okay, that's the standard differential of the free enthalpy. And so you can see that you recover the Gibbs-Duhem relation by saying that d mu water pure is equal to minus S, so it's the molecular entropy plus the molecular volume that I already introduced, because the molecular volume is the total volume of water divided by the number of water molecules. So I should be a bit careful here. I changed notation. I should say in the pure water phase and in the pure water phase, because otherwise you will be completely lost with the previous notation. So please put W everywhere. We are dealing with the pure water phase. Any question on that? That's called the Gibbs-Duhem relation. I'm sure you've met it in the past, which provides you the derivative or the differential here of the chemical potential. So now in my equation above, I know the derivative of mu water pure with respect to the pressure. It's called Vm, this guy. And so I find my relation. I know if I observe a certain thickness change between the two tubes, I'm able to calculate the concentration of oil droplets, which is an important quantity. Okay, so I end up with the following fact. So that is what we wanted. And so now we can estimate what is the number and size of the droplets. Okay, so what do we get at the end? Let me just, this is the important relation. So C, the concentration is rho GH over KBT. Concentration of droplets. So this relation basically is saying, I should have written it this way. This is the Van 't Hoff pressure. this is the ideal gas pressure for a collection of microscopic oil droplets. So this is osmotic pressure of this gas of droplets that is balanced by the hydrostatic pressure. That is the equilibrium of the U-shaped tube. Okay, so osmotic contribution and hydrostatic. And so in my situation, C is equal to the number of droplets divided by the total volume. So I end up with the relation that is providing the number of droplets in my situation. So rho GH KBT times V. And so we can estimate it now. What is the total number of oil droplets? So this is 10 to the 3, this is 10. H is the height difference, is 5 millimeters. KBT is typically 4 10 to the minus 21. And the volume V is 30 milliliters. Remember, this is this guy. So this is 30 10 minus 6 meter cube. Okay, 10 minus 3 to go to liters, and then again 1,000 factor to go to meter cube. So we end up with 3 10 minus 5 here. And so what do we get at the end? So 10 to the 4, 10, 10 minus 4, 10 to the 17. And what do we get in front? 5, well, something like that. Okay, a few 10 to the 17. This is the number of oil droplets. So you see, it's still a huge number. And if you want to put it in moles, this is 1 micromole, so 3 micromole. Because a mole is 10 to the 6, 10 to the 23, right? Okay. So that's the number. So when you prepare with 30 milliliters, like which is a typical number in your kitchen, when you prepare your vinaigrette, you end up with this number of little droplets of oil in the vinegar phase. What do we need now? We would like to calculate the number and size of the droplets. So the number and size of the droplet, I already got the number. So the size of the droplet, remember that the volume is something like that. So we can estimate A from the volume. And now we need the number, the total, the relation between the number and the volume. So the number of droplets times their volume is the oil volume that I put initially, which is 1.5 milliliters. If you remember my initial drawing, I was mixing oil and water. So I know exactly the quantity of oil I'm putting. The volume of oil didn't change by mixing, as I assumed. And so we have this conservation of matter. The number of oil droplets times the volume of one droplet should be equal to the initial volume. So it provides me that 4 pi 3 a cube should be equal to 1.5 10 minus 6 again, divided by n, and n is 3 10 to the 17. We just calculated it. All right, so now what do we get? We get something like 1.5 over 12, let's say, 10 minus 6, 10 minus 23. And then this is like 10 minus 24 or something like that, due to the 12 over 1.5, which means A is equal to a third of that, which is 10 minus 8, which is 10 nanometers. And that is a striking fact. We call that a microemulsion. In fact, it's a nanoemulsion. So typically what you would see is that your droplets, they can be as tiny as 10 nanometers in radius. So they are really nano droplets, okay? That's what we call a microemulsion. Okay, so that is it for the first part, and the first part was just a reminder. I'm sure you went through this calculation in one way or another. In particular, I think the important thing that you found previously in your studies is this relation. Okay, so I'm sure you know exactly what I talked about today, but it was important to go back through this because we are just refreshing your memory with the chemical potentials, the PT ensemble, and the osmotic pressure. And now we will move on to the stability of an emulsion, and then how to correct or improve the stability of this emulsion. So this is the novel part, I would say. So now we start with what we call the Ostwald ripening, which is the fact that if you have two droplets nearby, they will tend to assemble at some point to get into one single droplet with the double volume, which is larger. And at some point, you will do the same with other droplets. And then at the end of the process, you end up with your two phases that are separated. Okay, so that is called the ripening or coarsening. Okay. In French, this is a mûrissement d'une émulsion. So according to you, what is the reason for that ripening, that coarsening, that instability of the microemulsion?
That all the droplet doesn't have the same size.
Okay, so in my case, I'm doing really the ideal situation. I'm really considering, it's perhaps a fake problem, I agree, but I'm really considering that I have an assembly of identical droplets.
The droplets just want to reduce their surface.
Yes. So there is this tendency of this energetic cost, but we see that there is an entropic gain. But then your colleague has the good answer before. I'm really for now calculating everything with an assembly of small droplets like that. But at some point, if there is one which gets larger, that's exactly what your colleague said, what will occur? What do you get? If there is one droplet which is suddenly, for some reason, larger than the other. And I'm sure it's the case, it's a polydisperse life. What happens? I agree with you. If I would put the two in contact, the big and the small, then they would tend to form a single object to minimize surface tension. That was the last argument. But I mean, you need the droplets to meet each other, which is really a mechanical process. You need convection or something like that. I'm talking about a much more microscopic mechanism here.
The oil is there's a little bit of oil in the water, so it can just diffuse into the bigger.
That's exactly correct. Here, in fact, you have a mixture here as well, and so you have species belonging to the droplets that are also in the other phase. And as soon as you have a difference of sizes, you will change the surface tension term because it's related to the size, for instance, and so you will change the chemical potential. So there might be a gradient of concentration between the two regions of space. And so microscopically, the molecules, they will be driven by diffusion. That is why the fate of a vinaigrette is to become a separated oil and vinegar box, unfortunately. Okay, so let us now focus to understand that. It's exactly the thing we want to show. Let us consider a single droplet. So oil and water or water and oil is the same. So I'm just considering, let's say, water, because I was focusing on water so far as the main quantity. So let's consider a water droplet into oil. And let's assume that very far away, so it's a spherical problem for now, but very far away at R goes to infinity, I have an oil-water interface. If you want a super big bubble or droplet. So this is water. Okay, so you have oil, you have one single entity, which is really alone in the world. It's a water droplet. But very far away, there is a boundary where there is another water droplet that might be bigger. And so we consider that there is a flat interface. Or you have already a kind of phase separation and you have really a flat interface somewhere. It's the same. All right. So let's consider this situation, and we will calculate the chemical potential of the water molecules here, but also here, because as you just suggested, they are also slightly diluted in oil, even though they don't like each other, the two quantities. All right, so first of all, what is the chemical potential of water in the droplet? So here there is no more entropy consideration. I'm not. I see the droplet. It's like a big droplet in my vinaigrette box. So what is the only modification with respect to the pure chemical potential? I can start again. I have the pure water here. A priori, in this droplet, there is no oil molecules. But then what do I have? I have a change of energy, potentially, and a change of entropy. And I neglect it here because I have a single droplet. I'm not considering any positions otherwise. So there is no oil here. I'm just considering pure water droplets. What is delta E? What is the difference between being here or here? This would be pure water chemical potential. Let's say it's a reservoir of water. Here it's a droplet that has a shape with an interface. So we are back to the idea that there is a cost to this interface. So delta E is 4 pi A squared times gamma, the water oil surface tension. Right? So the chemical potential of water in the water droplet, mu of water, well, is the pure chemical potential if I derive this with respect to the number of water molecules. Plus, then there is 8 pi A gamma I derive with respect to A, and then the derivative of A with respect to the number of molecules. Of course, if I have plenty of water molecules, I have a large droplet. If I have not a lot of water molecules, I have a small droplet. So the radius of the droplet is related to the number of water droplets. In fact, by conservation of volume, I can say that I have a certain number of water molecules multiplied by their individual volume, which is the molecular volume. And this should be equal to the volume of the droplet if it's pure water. All right. So this guy is 3n water volume of a molecule divided by 4 pi to the 1/3. And so this guy is 3 Vm over 4 pi A to the power 1/3 times the derivative of n water to the 1/3, which is 1/3 n water to the minus 2/3. And I can just transform that by multiplying by n water to the 1/3 and by dividing by n water to the 1/3. So it comes back to A over 3 divided by n water. All right, so the chemical potential of water in the droplet is the pure one plus a correction, which is 8 pi A squared gamma over 3 number of water molecules. But there I'm not done because in AW there is A, right? So I should end up with a formula with only one variable. So I can, for instance, focus on the radius, which is the macroscopic observable. It's more interesting than NW here. So 3 and NW is 4 pi A cube over 3 divided by Vm. Okay. Okay, so what do we get here?
Sorry.
Yes?
In the expression for A, I guess there shouldn't be an A in the denominator.
Oh yeah, that's a good point. Thanks. And did I keep it here? And where again? Should be okay now, right?
Okay.
Thank you for the comments. Good point. And then I can also erase this guy and the power 3, and I end up with the final relation 2 gamma Vm over A. So it's an intuitive observation that the chemical potential of water inside this water droplet is higher than the one for a flat reservoir because you have an additional contribution to the surface tension. So there is a mechanical increase of the potential energy, if you want. This vanishes when A goes to infinity. So when you have a very large droplet, you kill this contribution and you go back to pure water, the reference. All right? Okay, that's the first side. So we now have the chemical potential of water here, just on this side of the boundary. And we would like now to have the chemical potential of water on the other side, in a sense. All right, so we assume here, and that's the thing, we assume here that this is pure water, but that we allow for some molecules of water to be diluted in oil. Okay, that was the mechanism proposed by you. And so we would like to calculate the concentration profile of those molecules in particular. So now we are interested, by assuming an ideal solution, we are interested in the chemical potential of the water molecules in oil as a function of their concentration. So we assume that there is a certain concentration and we would like to calculate so there is a certain concentration of water and we will basically place ourselves really near the boundary and we would like to calculate the chemical potential. All right, so this is question number, sorry, I'm a bit lost with the tutorial here. All right. So let us connect the chemical potential of water inside oil now to its concentration. So here we have the free enthalpy in the oil phase, which is a combination of pure water, pure oil, and mixing. And therefore, in the mixing, you have, as usual, an energetic contribution, an enthalpy contribution, because here there is no volumetric change, and minus Kb, minus T delta S, sorry. But now that I'm considering the water molecules here in the oil, there, of course, entropy matters because I'm not considering the single droplet as before, but now I have plenty of molecules that are scattered all around and they can really exchange positions and explore the phase space. So I have an important entropy contribution. So it's the same as before. In fact, I'm dealing with minus KBT, and then again, finding small n among capital N, right? And I will define the quantities now. It's exactly the lattice discussion before. So instead of considering a lattice of droplets or positions for droplets, I'm considering a lattice for molecules now. So it's a much smaller length scale, but the problem is the same. I still have a lattice. And so N is the number. So it's the volume divided by the molecular volume. So it's the number of cases in my lattice, but in molecular sense. N is the number of water molecules. And the total number n is the volumes divided by Vm, and the volume is what? Is the number of water molecules times the molecular volume of water plus the number of oils molecules, simply. And in fact, sorry, it should be a volume. So I'm lost here. So it's the molecular volume of oil. I introduce it here, which is at the end simply, and there is a ratio of molecular volumes, of course, if now I consider conservation of volume and not number, right? So the total number of cases in my lattice is the number of water molecule plus the number of oil molecules, but corrected with this ratio of molecular volumes, because at the end, what is conserved is the volume. Volume of water and volume of oil, all right? And they don't have the same molecular volume. So all that to say that small n, or n water, is both in capital N and in small n, but it is not in n minus n. N minus n is equal to n minus n water here, okay? And so n minus n water is equal to the number of oil molecules and the ratio of molecular volumes. So it's independent of the number of water molecules. So in fact, only those two terms matter in the entropy when I will derive now with respect to the number of water molecules. At PT and number of oil molecules fixed. So you have the first derivative, which is the derivative of the pure free enthalpy of water. So it gives me, again, the pure chemical potential. Then I have nothing into the pure oil. There is no water molecule in the pure oil. And then I have another term that I cannot neglect, which I don't know yet, but which is simply the derivative of the excess energy. So energy of mixing. And then I have minus kBT log n minus log n as before, and then the other derivatives, they cancel out. If I derive this, I get 1 over capital N, so it gives me +1, and this gives me -1. So I'm just left with this guy. And so finally, the chemical potential of water into the oil phase is the pure chemical potential of water, a shift due to energetic consideration at the molecular level, van der Waals-like, probably, and plus kBT log of the ratio between N and capital N. And so altogether, let me just copy paste it here. What did I say? kBT log N over N. And I can transform things into concentration by recalling that capital N is the total volume in units of molecular volume of water. And thus, the chemical potential the derivative of the excess energy of mixing plus kBT log of concentration times Vm, where I define the concentration as the number of water molecules into water, which is also in my notations here. Okay? Any question on that? All right, so we assume that the excess energy here is a quantity that is extensive in the number of water molecules. If I doubling the number of water molecules, I'm doubling the excess energy. This is not related to the interaction between water and water, but between water and oil. And so there will be a linear product in that sense, whatever the origin of this interaction. So this is independent. If I derive now with respect to NW, this quantity which is extensive in NW, this is independent of NW, and thus concentration. As a consequence, I can always rewrite that by introducing a reference scale of concentration plus kBT log of a ratio of concentration over C star, where C star is just the concentration C at which is equal to mu star. Up, for instance. The only dependency of C between being here. So that is now a different relation. Now water is considered as a solute and not the solvent. And so you recover the law from Baptiste, a log of concentration. For a solute, it's the log of concentration, and you cannot do a Taylor expansion as before, as for the solvent. So it's a different relation, exactly like for the Henry and Raoult laws in chemistry for the chemical potential. There is, depending on if you are a solvent or a solute, you don't have the same relation. There is a log or a linear relation. All right? Okay, so now it means that we know the chemical potential on this side of the boundary, and we knew it on the other side. So by balancing the two, assuming that you have a local and temporary equilibrium, if you want, really near the interface, you assume that you are at equilibrium, despite the fact that you are considering that there is a diffusion everywhere in space. You can assume that really at the molecular level nearby the boundary, you have a local equilibrium. This is what we will assume. And this is the next question, I believe. So we are at question number 3, and we would like to deduce the concentration field now from that. So we will assume that outside the droplet, you have this chemical potential. And inside the droplet, you have the pure chemical potential. Remember the law that we found. Plus a surface tension term, which is 2 gamma Vm over A. So this is the chemical potential inside the droplet, and in particular near the interface. And this is just outside the interface. Okay. So we can calculate the concentration near the droplet. We call this C. Actually, it's called CA. CA. It's C of R equals A. If I introduce a coordinate R, and if I recall the fact that the radius here is A, okay? And so I end up with a Boltzmann-like law for CA. It's equal to the exponential of two terms. So there is one term which is the difference of chemical potential. Sorry. Minus mu star divided by KBT. And exponential of 2 gamma Vm over KBTA. Thus, CA is equal to exponential, or I can C star exponential, sorry, it's C star here, exponential minus delta mu over KBT, exponential plus 2 gamma Vm over KBTA. And I introduce delta mu, which is the difference between the chemical potential inside the reference chemical potential inside the water, inside the oil phase, sorry, minus the pure case. And of course, this should be positive because the molecules of water, they prefer much more to be in the pure water phase than in the oil phase because they really don't like oil, okay? So it's necessarily a positive quantity, okay? Anyway, we found by balancing the chemical potentials on the two sides of the interface, as we did for the tube, but here at the border of a water droplet in oil, so here, we found the concentration profile just nearby. And it's called CA, and it's provided by some reference concentration here that we don't really control, but a correction related to gamma and the size of the droplet. So in particular, what happens here? What happens here? What is the concentration here? We call that C infinity. So really at a radius which is very far away from the center of the droplet and where you are meeting another droplet or a flat interface, whatever. What is C infinity? According to you? So the problem is the same. I could consider this interface as the one where I'm studying the chemical potential balance on the two sides of the interface. It's just that this has really an infinite radius, A. So I can take really the previous expression, but simply say that at infinity, I only have the first contribution, not the second one, because the radius is going to infinity, and thus the exponential becomes 1. Okay, so this is interesting because it means I don't really care about this prefactor here. I can just say that the concentration A, at point A, here, is just the concentration at infinity, meaning if you had a droplet that was very big, and a correction due to the finite size of the droplet. And you put all the unknown into C infinity. In fact, the amount of things that you don't know is strictly the same here and here. So since you are interested in the difference between the two, or the ratio between the two, there is a way to put all the dirt into C infinity. Of course, its very value will play a role in the diffusive flux, and we will have to remember that it's coming from a difference of chemical potential here. All right, but what can we conclude from that? That's important. Look at that expression. How does it compare to C infinity? Anyone? How is the concentration of water molecules in the oil phase here near the droplet compared to C infinity, the reference near an infinitely big droplet.
We can see that CA is larger than C infinity.
And
so,
thus,
so we can interpret that if a molecule is close to the interface, it will finally reach the interface and join the infinity phase. And so the concentration will be a bit lower close to the interface than in the bulk.
Correct. So you're really having the mechanism now to say why the small will empty itself into the big one, okay? At the diffusive level. You're saying that the concentration here is bigger than the concentration here. And so there is a flux, okay? And so the molecules, they are just biased in their diffusion process. They have a tendency to go more towards the bigger droplets than the smaller ones. So eventually, this will kill this guy because it will simply evaporate all his matter into the big ones. And so your vinaigrette will be transformed again into pure oil and pure vinegar at the end of the process. I'm sure you have experienced that already. Okay, so we have the two concentration, and so now we can rebound on your ID and try to calculate really the diffusive flux. Then we have everything at hand to do that. So I think it's the next question. We can first obtain the concentration profile everywhere and then deduce the flux. Up. All right, so we assume that we are quasi-static. That's an assumption. That is pretty sane if you consider your vinaigrette. Again, you have droplets that you can identify their size pretty well, and the diffusion of molecules is a slow process. Before those droplets change notably in size, you will have to wait hours, okay? So basically, we can assume that you have a diffusion process that is quasi-static, and therefore, that this relation can be simplified, which is the diffusive law, can be simplified like that into a Laplace equation, simply. So you have to solve the Laplace equation in a 3D world with an isotropic symmetry, spherical symmetry. So this is the radius. That's the Laplacian in spherical coordinates for a quantity that only depends on R. And so I can solve this equation for finite radiuses, this goes away. I end up with R squared C prime is equal to constant. And thus C, which is constant over R plus another constant. That's the concentration profile. But the good thing from what precedes is that I now have identified two boundary conditions. One in the near field, near the droplet, and one in the far field, near the larger droplet, if you want. So this can be viewed as C infinity plus CA minus C infinity over R, and I need a size A. So that's my C of R. When R goes to infinity, I kill this term and the concentration reaches the infinite concentration. When R reaches A, those vanish. C infinity cancels this infinity, and I reach CA, which is the other concentration. Okay. So I've simply used the two boundary conditions into this very simple concentration profile. Good. So I know at every position in space between the small droplet and the big one or the reservoir, I know the concentration profile. It goes like 1 over R. So it's big near the droplet and it decreases with 1 over R low towards the infinite region. Now, what is the flux near the droplet? So it means, as you suggested, there is here more water molecules than here. And so there is a flux. My question is, what is the flux here, J, A, of molecules of water? So how can I get the diffusive flux from the concentration profile?
Okay, so it's just the flux is just minus the derivative of the concentration at the border, so at A.
Yeah, correct. So if I just take its norm, it's a radial diffusive process, it's isotropic. So the norm is, in general, the diffusive coefficient is, the diffusive flux is minus the diffusion coefficient times the gradient of concentration. So I can call it like that. So let me just come back to this first. This is Fick's law. All right. And so I'm in radial coordinates, and so I'm just writing this like that, which is provided by the law I just obtained. So there is a minus CA minus C infinity over R squared times A. And it is positive. At any position in space, it's positive. So there's really evaporation of the droplet. Its matter is diffusing away. So I can now estimate this at R equals A. So this is R equals A. It's a particular point. It's really near the interface of the small droplet. And so I end up with this positive flux divided by A. So this flux, its dimension, as you can see from here, it's 1 over a volume and the length. So it's 1 over L squared, a length squared and the time. Now I need to integrate that over the surface of the droplet to get the change of matter per unit time. Okay, the decrease of the number of molecules per unit time. So dN water versus dt, which is the derivative or the variation of the number of molecules of water due to the diffusive process, is equal to minus this loss, so minus JA, integrating over the whole surface, but it's a radial flux, so it's simply this product. And so I end up with minus d CA minus C infinity, okay, divided by or multiplied by A and 4 pi. There's a time miss. No, it's okay. Yeah. And now I want to close the problem by remembering that the number of water molecules is related to the size. Okay, the larger the droplet, the larger the number of molecules. So again, we have this relation that the number of water molecules is related to the volume. So if I multiply this with the molecular volume of water, I end up with the total volume, which should be equal to the volume of the droplet. So N dot is 4/3 pi over Vm times 3a squared a dot, the derivative of the radius with respect to time. So this is 4 pi a squared over Vm times a dot, and it should be balanced. Remember what is the expression of that guy? It's a 4 pi d there is a minus Ca minus infinity. Which can be simplified further into, so sorry, I will just write that. A dot is equal to minus d Vm CA minus C infinity. And where we should remember what is C minus infinity. So CA was C infinity exponential, let's come back to CA, C infinity exponential 2 gamma Vm over kBTA. Okay. So I found the evolution, the relation for the evolution of A in time. Or generally speaking, I should write it this way. So this I can solve numerically. Okay, this will provide me the evolution, the fate of my my water droplet in oil. All right, so I think the next one part is to solve that. And for that, we will assume that we are in the large temperature limit, which is equivalent to, say, the large droplet limit. So we can linearize that guy into simply the linear term. So it's either the large droplet limit or the large temperature limit, okay? And you can put number to see when this is valid, okay? The thing is that this equation, you can solve it numerically, so there's no problem to do the general situation. I just want to give you the main features of this by going to the easy linear case for the analytical part. All right, as usual. So this becomes minus d Vm over A squared times 2 gamma Vm squared kBT. And thus, it's an equation on A cube, in fact. So you have A squared A dot. I think there is a factor 2, and what else? 2 gamma Vm squared over kBT. That's it. So I can integrate that with respect to time. It says that A3 over 3 is equal to an origin at t equals 0 minus 2d gamma over kBT times time. And I can, if I want, well, I will do it at the next line. A cube is equal to A0 cube 1 minus 6t Vm squared gamma over kBT A0 cube times t. Okay. Stated differently, I can write A of time, which is the initial value, times 1 minus t over a certain time scale to the power 1/3 in dimensionless units, right? Which can be first, so I will discuss tau later, but which can be plotted this way. A over A naught starts at 1, and t over t naught ends at 1, and you have something like which is a third order polynomial, okay? So the droplet will disappear eventually, okay, in a finite time. It's not, you know, you don't have a decay over time and time. No, it's in a finite time, and you can compute that finite time from a linear argument. Of course, things are a bit modified if you go numerically to the nonlinear case, but you can do it and discuss the results. And the important physical point is the following: is that the time scale has been defined as kBT over A naught squared, A naught cube, sorry, 6D. So that's the exact formula, and we will do some simple scaling on it. So we will forget the prefactors. It goes like the initial volume, basically. KBT will disappear because I remind you that we have the Stokes-Einstein relation at equilibrium. So the typical diffusive coefficient is related to KBT and the friction coefficient in your Langevin equation, 6 pi, the viscosity of the fluid times the size of the molecule, where B is simply, let's say, well, it's not exactly that, I will do it in scaling, is the molecular volume to the 1/3. So if you want, it's the radius of a water molecule. So I can say that this is B6 gamma. And something is missing, eta. Do you agree with that? So it's a B5.
Just, isn't there a C infinite in factor?
Oh, yes, somewhere. Yes. Also for dimensions, right? So it's here. It has disappeared here. So each time there is a D, there should be a C infinity. Sorry for that, and thank you very much. Here it's okay. Here there is a C infinity at the denominator. Is it better? Yes?
Yes.
Okay, thanks. Good catch. So we end up with a time scale that depends on several interesting quantity. The initial size. So the larger the initial droplet, the larger the time scale for vanishing. So it goes in, it accelerates, I mean, it increases the message. The small droplets, they tend to diffuse and go into larger droplets, and the larger droplets, they are stable on the longer time scales, okay? However, the process is slower if you have a viscous solvent, but I mean, for vinaigrette, we cannot change too much the viscosity, right? But still, there is a change with the viscosity. So if you increase the viscosity of the solvent, you stabilize your microemulsion. An interesting aspect comes from gamma. If now you add surfactant, like mustard, for instance, that stabilize the droplet, that will diminish its surface tension, you will increase the time scale, so the stability. This I cannot play too much. It's the size of a water molecule, so I won't comment further. This I already commented. And C infinity, let us remember what is C infinity. It should be given somewhere. C infinity is a concentration of reference. It can be 1 mole per liter, so it's meaningless. But you see that there is here something which is positive. So there is the temperature dependence that is important. C infinity increases when the temperature increases. There is a minus sign, a positive quantity, and the inverse of temperature. So it's really increasing with temperature. So it means if I take my vinaigrette and I just warm the sample, I will increase C infinity, and so I will decrease the time scale. So it will be dramatic. So if I want to conserve my vinaigrette, I should put it rather in the fridge than in the ambient, okay? I mean, diffusion is accelerated with KBT, you could say, but KBT is here killed in this process. There is no more KBT at the end. So it's not related to that. It's related to the chemical potential, the difference of chemical potential. All right, so we are done. So what does it mean? It means that this is not very interesting. What is very interesting is this one. Is that if you put mustard or if you put some surfactant into your vinaigrette, you will stabilize it. So please don't forget that, apart from the taste. But the problem is that you know that when you add some surfactant, at the most, you will reduce the surface tension by how much? Do you know the typical order of magnitude? If I am in a lab and I want to reduce the surface tension, I add some surfactant into my solution. Well, the best I can do typically, of course you have some special cases, but typically is to reduce it by a factor 2. So for instance, the water surface tension will become 30 or something like that. So it's pretty bad. Is I can just change the time scale by a factor 2. It won't save my vinaigrette, okay? It's dead anyway. So is there a way to really stabilize it for good? Meaning transform this curve here into a curve that's stabilized at a finite value here, which is, let's say, different from 0. Which can be epsilon-esque or whatever, but that's higher than 0. Can we stabilize it and find a smart way to do that? And this is the essence of the article by Webster and Cates. I say, well, you have to add a species inside the droplet that is stable only in the droplet. So of course, if I put salt in the vinaigrette, for instance, salt is charged. It lacks very much water, and it hates oil. So it will stay in the water. And so when the water droplet starts to reduce in size, well, at some point there is a problem because you will need to expel those salty particles or ions into oil, and this is bad. So there will be a stabilization mechanism, and that's what we want to quantify now into this final part. Feel free if you have any question on what we did so far. Is there any comment or question? Okay. So the stabilization part now. So now we are doing exactly the same as before. I have a water into oil. I have far away a huge water droplet, or if you want an interface with a reservoir at infinity. But now the big news is that I say, well, I've added an ideal gas, if you want, of particles that are solutes for water. Could be salt. And I put a large number of those, P, inside the droplet. So does anyone see the relation that will provide me the final radius of my microemulsion, of the droplet, of the typical droplet of my microemulsion? What balance do we get now? The driving mechanism for the Oswald ripening was, I mean, the mechanism was diffusion, but it was biased diffusion due to an external force or external potential energy. And this external potential energy was the surface tension, was gamma. Okay, so the thing that will kill your vinaigrette is the surface tension, right? So clearly there is a problem with gamma. And the fact that you are adding some solute inside the water will fight against gamma. So what is the effect that I should take into account now? What is the balance? If you remember the YouTube that we considered before, the balance was between gravity, that tends to stay the two levels the same, and osmotic pressure that tend to increase the height of the microemulsion region. So there was osmosis against gravity. Here, there is surface tension against adding solutes brings what kind of force or effect?
Again, osmotic pressure, since the third species want to be in more space.
Yes, so they would like to have a large entropy, those salty species, if I may, and so they would like to have a big volume, so they like to have a big water droplet so that they can explore plenty of configurations and thus have plenty of microstates corresponding to a macro state, and thus a very favorable situation on anthropic contribution. Indeed, so what we would like to say is that, well, the capillary pressure will balance, or will be balanced, will be fight by the osmotic pressure, that's it. And just without any calculation, we can predict the final radius. The capillary pressure is gamma divided by the typical, or multiplied by the typical curvature, which is divided by the typical radius that we consider. And this will balance what? The osmotic pressure. And the osmotic pressure is, if I think about the dilute assembly, the Vento flow, we already discussed that. Well, I have KBT times the concentration of species. So here I say that I have P species into the volume A cube. So I end up with A squared, which is KBTP over gamma. In other words, I have A, which is the ratio between KBT over gamma, which is a typical length scale, times square root of P. This is, let me call it A equilibrium, because now we have a real equilibrium for our vinaigrette. And I can always say that gamma is something like KBT per unit of a certain molecular surface, okay, or van der Waals interaction per unit of B squared. And so this is typically corresponding to a length scale, which is a molecular length scale, so the size of a water molecule, for instance. So if you put a lot of solutes or ions in your solution, well, this is much bigger than a molecular radius. So it means that you're able to stabilize your droplet with a size that is really mesoscopic. It has plenty of water molecules inside, provided that P is sufficiently large, so that you put a lot of salt here. Okay, so now we have all the ingredients here. We would like just to modify the previous equations, including the diffusion, biased by surface tension, and by osmotic contributions. And we would like to find the complete equation that you can solve numerically if you are interested. So the idea is to again, come back to the microscopic description and think about the chemical potential near the interface. So what is now the chemical potential inside the droplet? Inside the droplet, the chemical potential of water has been modified. Well, before the addition of the salt, I already knew that it was something like pure water, and then there was a contribution due to surface tension, which was what? Don't remember it in detail. It was something like, what's here? 2 gamma Vm over A without the KBT of Boltzmann. 2 gamma Vm over A, right? Correct me if I'm wrong, but that was the case with when P is equal to 0, when there is no added species. Okay, and now I'm adding a dilute species. It's a dilute solute. So to summarize, I'm considering the chemical potential of the solvent in presence of a dilute solute. So I think we wrote that at some point. For another problem, what was the chemical potential of water in presence of a dilute solute? I think it was the first problem where we had water in presence of a dilute oil, and we found the chemical potential of water to be, let me see, this. There was this linear correction in concentration when water is the solvent. So here it's the same. We will use it. The chemical potential of water is the reference one minus KBT times Vm concentration. So there is a minus here. Minus KBT times Vm, the molecular volume of water, times the concentration of what? Of solute. In the first problem, it was the oil droplets that were the solute. Here, it's the salt. So the salt is, the concentration is P divided by well, the volume. Okay. Do you understand what I wrote? I simply used the formula for the chemical potential of water when it is a solvent now. So when the chemical potential when water is a solvent, you have a reference contribution. So in our case, it's not only the pure case, but it's the pure case corrected with the fact that I have a finite curvature here. That's the same, minus a correction due to the solute. And we show that when we are dealing with a solvent, the correction is linear in concentration. There is no log. So it was minus kBt, the concentration, and the molecular volume of water. And so the concentration of solute is simply the number of solutes divided by the volume of the droplet. All right? But basically, you see, we just shifted the chemical potential a bit. We reduced it, so we stabilized the droplet if we reduce the chemical potential. So it will simply change all the formulas that we had so far, and so we will not write all of those. We again assume that everything is valid, that we have a quasi-static concentration profile, that we have a diffusive process from the small droplet to the big one, and we have an equation that is here. Let me come back to it. That is this one. And I will just copy paste it. So it's the same, but simply now you not only have a destabilizing surface tension term, you will have in addition a stabilizing osmotic term. Okay, let me write it. So you have A dot is equal to minus D Vm over A. C infinity, and then you have the exponential gamma Vm over A kBt. That was this term. Now you have another term, which is this one, Vm P 4 pi A cube over 3. kBt cancels out, and then minus 1. So let me just check that I didn't forget anything here. Sorry, it's here. What do I get? It's here, sorry. dVm over A C infinity, yes. Do you agree? So from what we did, it's exactly what we did so far by calculating the diffusion profile, I mean the concentration profile and then the flux, except that now we have shifted the chemical potential of the droplet by this solute term that is additional, that is new. Okay, but again in the high temperature limit or in the large size limit, we can simplify it. So I think it's still question number 3, yes. So we will linearize again the term. And then I end up with 2 gamma Vm kBt A minus Vm P. And I can also absorb the A in front here. All right, so this is the new equation in presence of P solutes. It contains in particular the previous equation when P equals 0. So it's exactly the same physics. You can just compute it numerically. You can solve the linearized equation that we just wrote if you're interested in that. But we immediately see that there is a stable solution. This being equal to 0, this is the equilibrium configuration, is possible for finite A value when 2 gamma Vm over kBt is equal to 3 Vmp over 4 pi A squared. And I can even remove the Vm. Okay. And so I end up with what? With 8 pi over 3. So the equilibrium value, EEC, is equal to the same as before. It's KT over gamma, square root of P, but then there is a prefactor, which is meaningless. 8 pi, sorry. It's 8 pi over 3. But basically, it scales exactly as what we found before. It goes like the square root of P. So we recover the intuition, and you can solve that equation and study it as you wish. So now you've stabilized your emulsion, and so your vinaigrette can last forever. All right. So I think we are done with this. We are a bit in advance, but it's fine. Do you have any question before?
Yes. Is it legitimate to linearize with respect to VMP over 4 pi A cubed 3?
Yes, not necessarily. Not necessarily. So I should have called that large A limit instead of a large T.
Okay.
Sorry. Again, my point is not to claim that there is validity or not validity for those equations. My point is that we found the exact expression here, and that if I was in the lab, I would solve it numerically, right?
Yeah, sure.
Okay, so I want to give you features now, but
okay.
you're completely right. Thanks. Any more comments? No? All right, so thank you very much, and I wish you a very good week. Last tutorial is next week, and we will come back to polymers and deal with the dynamics of those polymers. Okay, so thank you very much.
Thank you. Bye.
Bye.
Bye, everyone.
Bye.
Bye.
Bye.